How do you write robot algorithms using sensors? Imagine a robot that can see, hear, and feel just like us. How does it do that? The secret lies in writing smart instructions that tell the robot how to interpret what its sensors detect. When you understand this process, you can create robots that respond accurately to their environment. Sensors are tiny devices that pick up physical signals like distance, light, sound, or touch. For example, ultrasonic sensors measure how far away objects are, infrared sensors detect obstacles, cameras give visual information, gyroscopes tell the robot which way it is facing, and touch sensors sense physical contact. These sensors produce raw data that needs to be processed before the robot can understand it. First, you need to decide what the robot is supposed to do and where it will operate. For example, a cleaning robot must navigate around furniture, while a delivery robot might follow a specific path and avoid obstacles. Next, program the robot to read data from its sensors regularly. This involves setting up the microcontroller or processor to collect sensor signals at fixed intervals. Since raw data can be noisy or inconsistent, you often need to filter it. Techniques like averaging multiple readings or setting threshold values help make the data more reliable. Once you have clean data, the next step is to interpret it. For example, if the ultrasonic sensor detects an object very close, the robot might need to stop or turn away. If the infrared sensor sees a line on the ground, the robot can follow it by adjusting motor speeds. You use decision-making structures like if-then-else statements or switch cases to evaluate sensor inputs and decide what to do next. After deciding, you translate these decisions into commands for motors, servos, or other actuators. For example, if an obstacle is detected, the robot might stop and turn left. If a line is detected, it might keep moving forward along the path. Control loops are essential for making the robot respond in real time. These loops constantly check sensor data and adjust actions accordingly. Feedback mechanisms help the robot correct its behavior, like maintaining a set distance from a wall or balancing on uneven surfaces. Proportional integral derivative controllers are common tools that fine-tune responses based on sensor feedback. Testing the robot in real or simulated environments helps you see how well your algorithm works. Adjust thresholds, timing, or control parameters to improve performance. Using debugging tools and visualizing sensor data makes it easier to see where adjustments are needed. Robots use sensors for many practical tasks. Autonomous navigation relies on sensors like LiDAR, cameras, and ultrasonic sensors to map surroundings and avoid obstacles. Line-following robots use infrared sensors to stay on a track. Sensors also help robots identify objects for picking or sorting. Balancing robots depend on gyroscopes and accelerometers to stay upright. In short, writing robot algorithms with sensors involves gathering data, processing it, making decisions, and controlling actions. This process allows robots to understand and react to their environment intelligently. Learning these steps is key to building robots that can adapt and perform complex tasks.